All right, thank you. There was a change in the program. Runtime verification is probably known for its security audits with emphasis on formal verification. We were, for example, the company that audited the first version of Uniswap or the ETH2 deposit contract, where we prove that these programs are actually correct using mathematical techniques. But today, I'd like to discuss a vision that we have, how to extend formal verification into something a lot bigger that can have a big impact on the blockchain space. And we call this universal truth framework. So what is that? So a universal truth framework, the way we think about it, is a framework in which every claim that is being made is verifiably true. That means that every claim comes with an independent, small, succinct, third-party checkable proof certificate. So you don't need to trust the maker of the claim. You don't need to trust runtime verification. You don't need to trust the developers. You don't need to trust yourself. Everybody can check the claim. And what is a claim? So a claim can be anything that is provable or computable. For example, the execution of a program. We make a transaction. You call a function in a program, in a smart contract. That is a claim. I'm making the claim that this program does this thing with this input. Same is a particular work or action that is being done. Or a security audit, when we claim that Uniswap has been formally verified and it is correct. Unfortunately, in the world of security auditing, we still present PDF documents to our clients, and that's the correctness argument. That needs to change, right? So we can present actually proof certificates that can be checked, so you know exactly what is being claimed by that audit. And so are mathematical theorems. Actually, in fact, what I'm going to say next is that every claim is in the end a mathematical theorem, right? A claim that holds under certain assumptions. And now the user can simply trust the claim, because the user can check the certificate. Okay, so the claim comes with a certificate, you check the certificate, you know the claim holds, for sure. So how can we implement this? Right, because this is very powerful. If you have such a framework, then you have verifiable computing, you have everything that we can do with zero-knowledge proofs, you have trusted blockchains, you have a lot of advantages. But is this feasible? Is it possible? How can we do this? And this is our vision. So we want to combine or marry the K framework that we use in our security audits to do formal verification and other activities, rigorous activities. We want to combine that with snarks. Specifically, you can think of K as some sort of brain, some AI, some automated tool. Actually, K is based on automated reasoning, has lots of automation to find proofs for you. And in the end, you can think of K as something that takes as input. By the way, do I have 15 minutes or how much time do I have? Because my talk was not supposed to be now. Hey, Queenie? Somebody? Queenie? Roy, my talk is 15 minutes or is longer or shorter? Still 15 minutes, okay, all right. So the K framework that we use for audits and verification will take a claim as input, very, very simplistically speaking, and generate, after a lot of work and automation and possibly interaction with the user, will generate a mathematical proof. And we make a distinction between a mathematical proof and a cryptographic proof. A mathematical proof is the good old-fashioned mathematical proof, where you infer every step from either axioms or previously inferred steps. And these proofs tend to be very long, but very precise, very precise. The advantage of having very precise proofs, mathematical proofs, is that they are very easy to check. And indeed, we have developed recently a proof checker that has only 240 lines of code. Okay, so with 240 lines of code, you can check any claim that comes with a proof, with a mathematical proof, and the K framework can produce such proofs. All right, again, simplistically thinking, with these 240 lines of code, you can check any claim about any program in any programming language. I know it may sound excessive, but it's not. You can go to our research webpage and find papers and evidence substantiating that claim. And now, what we are working on, and I hope that it will be done soon so everybody can use it, is to snark this proof checker. So instead of having this long proof that you have to present to your users, you present a very succinct proof of 256 bits or some constant number of bits that everybody can check independently. So this way, you start with a claim and end up with a very succinct small certificate, and that is an absolute guarantee that the claim is true. This has many applications, but one of the most intriguing and interesting applications is one where we can build new blockchains, a new generation of blockchains based on this idea. Because we can have a blockchain of truth, how we like to call it, in which every single claim made on a blockchain is actually true because it has been proved true and certified to be true. And we can write smart contracts in any programming languages because the programming languages play no role anymore. You don't have to have a programming language hardwired to a blockchain, like an EVM-based blockchain. And the idea in the end is that with the K framework, we generate a mathematical proof, and then with the snarked proof checker, we generate a cryptographic proof on top of it. Right? So one way to think of this is like proof of proof. Right? So you have a proof, a cryptographic proof of a mathematical proof of correctness. So the absolute ultimate proof. All right, so time flies. I cannot really go deep into K. What I can tell you is that K addresses a very real problem that we have in programming languages and formal methods, namely that we have a lot of languages and a lot of tools to do a lot of things. And there are lots of systems combining languages and tools and applications. These come with pain points, both for developers of these tools and languages and for users, us. Developers have to reuse a lot of, actually duplicate a lot of code. They waste talent implementing the same tool for different languages. But what's worse is that all of us, we just have to trust this complexity. Why would you trust the Solidity compiler? You just trust it. Okay? So we want to change that. And actually, K was created to address these problems. First, it separates completely languages from tools. You plug and play your language and you get the tool. And everything that K does, everything that these tools do, for example, an interpreter, like EVM, Ray mentioned that we have a semantics of EVM, KEVM. We have a semantics of EVM, and we can run EVM programs, same like with any other interpreters of EVM. Right? So those are generated, it's one of these blue, the first blue box over there. It generates an actual interpreter, which also, when we execute it, generates a proof, mathematical proof, which you can check, which confirms that that execution is correct, according to the mathematical definition of the programming language. And same for deductive verifiers and everything. So K was constructed to address these two problems, to disconnect languages from tools and to give a mathematical proof object, a mathematical argument of correctness for everything that it does. K is very complex, has more than 500,000 lines of code in 4 different languages. It's very hard to trust it. You shouldn't trust it. See, any system larger than 1,000 lines of code has bugs, most likely. Okay, so that's our experience. So K has bugs, for sure. But we have a very rigorous mathematical foundation underlying K, which allows us to generate correctness certificates for everything that K does. And not only K, actually. This mathematical foundation is more, 10 more minutes? It's 10 more minutes. Excellent, thank you. Wow, that's the trick. You extend your. All right, so then I can talk later. No, I'm kidding. So we developed this logic, matching logic, as a foundation of not only K, but computing in general. Also a formal verification. So there are several other frameworks like K, for example, Coq, Lean, and all of these in the end produce mathematical proofs. And we need a language to express these mathematical proofs. Okay, so we need a formal logic to express all these mathematical proofs. And this is what matching logic is. You can think of matching logic as a language of proofs. Right? You need to express proofs in some language. So matching logic is the language of proofs. And it has the advantage, and it has been created in this spirit, that it is very small, very small. So you can write it on a napkin. So this is the entire logic, what you see here on the right. So with this logic, you can write proofs. This is a proof system in a logic, not cryptographic proof system, a logical proof system. With this proof system, you can check any proof of any claim of any program in any programming language. Okay? Let me put it this way. And it's so small, which means that we can implement a very small proof checker. And we have done that using MetaMath. MetaMath is a language to define mathematical theories and to mechanize proofs in these mathematical theories. It has lots of implementation. It's a very small language, has a big advantage compared to other similar competing frameworks. It's a very small one, it's very small meta language. There are more than 20 implementations out there, some of them even on hardware, FPGAs. And we define the entire matching logic in MetaMath in only 240 lines of code. So the definition of the implementation of matching logic in MetaMath looks something like this. And this is actually already 10% of the definition. Right? It's 10 times longer than this, and that's it. And then, once you have this, now you can take any mathematical proofs, and they will look like this, and send them to the MetaMath checker, which is very fast, and it will check them very, very efficiently. All right, so that's the idea. But now the problem is that these proofs can be huge. So we started a project together with Andrew Miller, who is a colleague at the University of Illinois, and with RISC-0, Tim Carstens, and some others from RISC-0, to actually snark this proof checker. So all this code now is being snarked. We implemented it in the Rust, and then compiled to the RISC architecture, RISC VM. And basically, we can generate snarks for mathematical proofs. Okay, I know it looks a bit longish and complicated, but it works. And in the end, getting back to the big picture and wrapping up, what our vision is that we can have a future in which all the tools will generate not only claims, like this program does this, or this smart contract is correct, or this does that, but also correctness proofs, proof certificates that are very small and very easy to check. And based on this, we can build not only the obvious, like having certified security audits, which is the easy application, but also entire blockchains based on the same principle where correctness of programs and correctness of executions live together. It's all about correctness in the end. Thank you.